Today we are going to discuss example of determination of absolute entropy of a gas, experimental verification of the third law of thermodynamics and residual entropy. In continuation, we are going to discuss an example of determination of absolute entropy of a gas. Suppose it is required to determine absolute entropy of a gas at 25 degrees Celsius under atmospheric pressure. This would be equal to the sum of the entropy changes involved in the different processes, each of which is brought about reversibly. It is assumed for general discussion that the substance in solid state exists in two allotropic forms, alpha and beta. The first step is heating the crystalline solid from absolute 0 to temperature T star, where T star is the temperature between 10 Kelvin and 15 Kelvin, and evaluating the entropy change with the use of Debye's theory. Let the entropy change be delta S1. Then delta S1 will be equal to the integration of A T cube divided by T dt within the limits 0 and T star. This will be equal to 1 by 3 A T star cube. The next step is heating the crystalline solid from T star to T Tr, where T Tr is the transition temperature at which the crystalline solid changes from allotropic form alpha to allotropic form beta. The entropy change in this process would be given by delta S2. Now, delta S2 will be equal to integral of Cps alpha divided by T dt within the limits T star to T Tr. Here Cps alpha is the heat capacity of the allotropic form alpha. Transition of solid from allotropic form alpha to allotropic form beta at the transition temperature T Tr. The entropy change in this process is given by delta S3, which will be equal to delta H transition divided by T Tr, where delta H transition is the enthalpy of transition and T Tr is the temperature of transition in Kelvin. Next step involves heating the solid in allotropic form beta up to its fusion temperature represented by Tf. The entropy change in this process is given by delta S4, and delta S4 will be equal to integral of Cps beta divided by T dt within the limits T Tr and Tf. Here Cps beta is the heat capacity of the solid in allotropic form beta. The next step will involve the changing of the solid in the allotropic form beta into the liquid state at the fusion temperature Tf. The entropy change of this process is given by delta S5, which will be equal to delta Hf divided by Tf. Here delta Hf is the molar heat of fusion of the substance and Tf is the fusion temperature. Delta S5 will be known as entropy of fusion. Now the liquid will be heated from its freezing point to its boiling point. The entropy change involved in this case is given by delta S6, which is equal to integral of Cpl divided by T dt within the limits Tf to Tb. Here Cpl is the Cp of liquid, Tf is fusion temperature and Tb is boiling point. In next step, the liquid will be changed into the gaseous state at the temperature Tb. The entropy change involved here is delta S7, which is known as entropy of vaporization and is given as delta S7 is equal to delta Hv divided by Tb, where delta Hv is the heat of vaporization per mole of the substance and Tb is the boiling point in Kelvin. Next step involves heating the gas from its boiling point Tb to the required temperature, that is 25 degrees Celsius. The entropy change involved in this process is given as delta S8, which is equal to integral of Cpg divided by T dt within the limits Tb and 298.15 Kelvin, where Cpg is the heat capacity of the substance in the gaseous state at constant pressure. Delta S8 is evaluated by plotting Cpg versus natural log T between temperature Tb and 298.15 Kelvin and noting the area below the curve. The absolute entropy of the gas at 298.15 Kelvin, that is at 25 degrees Celsius, which is represented by St, is equal to the sum of all the entropy changes listed here. Therefore, delta St will be equal to delta S1 plus delta S2 plus delta S3 plus delta S4 plus delta S5 plus delta S6 plus delta S7 plus delta S8. This method of determination of absolute entropy of a substance can be better understood with the help of some problems. Here is first problem. Cv for uranium metal is 3.04 joules per Kelvin per mole at 20 Kelvin. Calculate the absolute entropy of the metal in joules per Kelvin per mole at 20 Kelvin. We know that by Debye's T cube law that at low temperature in between 0 to 20 Kelvin, Cp is equal to Cv and it is equal to A T cube. Therefore, A will be equal to Cv divided by T cube. As the value of Cv and T are given, we have A equal to 3.04 joules per Kelvin per mole divided by 20 Kelvin whole cube. This is equal to 38.03 into 10 to the power minus 5 joules Kelvin to the power minus 4 per mole. Hence, Cp is equal to At cube is equal to 38.03 into 10 to the power minus 5 joules Kelvin to the power minus 4 per mole multiplied by T cube. Now, from the equation, ds is equal to St equal to integral of Cp by T dt within the limits 0 to T star will be equal to integral of At cube divided by T dt within the limits 0 and T star, and that will be equal to 1 by 3 A T star cube. As T star is 20 Kelvin, therefore, ds will be equal to integral of 38.03 into 10 to the power minus 5 joule per mole Kelvin to the power minus 4 T square dt within the limits 0 and 20. Therefore, S20 minus S0 will be equal to 38.03 multiplied by 10 to the power minus 5 joules Kelvin to the power minus 4 per mole multiplied by 20 K cube divided by 3, or S20, that is entropy at 20 Kelvin, is equal to 1.01 joules per Kelvin per mole, as you know that entropy at 0 Kelvin is equal to 0. There is another problem to understand the calculation of absolute entropy of a liquid. The problem is the heat capacity Cp of a substance is given by the following equation. Cps is equal to 16.74 into 10 to the power minus 5 T cube. T is in between 0 and 50 Kelvin, and Cp of solid equal to 20.92 when temperature is in between 50 and 150 Kelvin, and Cp of liquid is equal to 25.10 when temperature is in between 150 to 400 Kelvin. At the melting point, that is at 150 Kelvin, delta H fusion is equal to 1255.2 joules per mole. Now, calculate the absolute entropy of the substance in the liquid state at 300 Kelvin. Now, delta S1 will be equal to integral of Cps divided by T dt within the limits 0 and 50, and substituting all the values and using the Debye T cube law, we will have delta S1 equal to 6.97 joules per Kelvin per mole. Now, delta S2 will be equal to integral of Cp by T dt within the limits 50 and 150 Kelvin. We will have 20.92 joules per Kelvin per mole natural log of 150 divided by 50. On calculating, we will have delta S2 equal to 22.98 joules per Kelvin per mole. Delta S3 will be equal to delta SF, which is equal to 1255.2 joules per mole divided by 150 Kelvin, which will come out to be 8.37 joules per Kelvin per mole. Delta S4 will be equal to integral of Cp by T dt within the limits 150 and 300, which will be equal to 25.10 joules per Kelvin per mole natural log 300 divided by 150, and on calculation we will have delta S4 equal to 17.40 joules per Kelvin per mole. Hence, delta S, which is equal to St minus S0, will be equal to delta S1 plus delta S2 plus delta S3 plus delta S4. Therefore, St will be equal to 55.73 joules per Kelvin per mole, as you know that entropy at 0 Kelvin is equal to 0. These were the applications of third law of thermodynamics. Now we will continue with experimental verification of third law of thermodynamics. The heat capacity and enthalpy data on substances that exist in two different crystalline forms may serve to verify the third law of thermodynamics. For reversible isothermal transition alpha to beta, we can write according to third law of thermodynamics, delta S is equal to entropy of beta form minus entropy of alpha form, which is equal to delta H Tr divided by T Tr, where delta H Tr and T Tr are the experimentally determined enthalpy of transition and the temperature of transition respectively. Now, delta S will be equal to S0 of beta plus integral of C Ps beta divided by T dt within the limits 0 and T minus S0 alpha minus integral of Cps divided by T dt within the limits 0 and T Tr. This is equal to delta H Tr divided by T Tr. If an experiment proves that integral of C Ps beta divided by T dt within the limits 0 and T Tr minus integral of C Ps alpha divided by T dt within the limits 0 and T Tr is equal to delta H Tr divided by T Tr, then it will also prove that S0 beta is equal to S0 alpha, that is entropy of beta form at 0 Kelvin is equal to entropy of alpha form at 0 Kelvin. Thus, both the crystalline modifications alpha and beta would have equal entropies at 0 Kelvin in accordance with third law of thermodynamics. Experiments carried out on systems such as sulfur, tin and phosphine have demonstrated the validity of the third law. The following results have been obtained on phosphine. Delta S Tr is equal to delta H Tr upon Tr equal to 185.7 divided by 49.43, which is equal to 15.73 joules per Kelvin per mole. In respect of phosphine, the difference of the two integrals in this equation is experimentally found to be 15.69 joules per Kelvin per mole. That is, integral of Cps beta divided by T dt within the limits 0 to T minus integral of Cps alpha divided by T dt within the limits 0 and T Tr is equal to 15.69 joules per Kelvin per mole. A comparison of the two results shows that within the limits of experimental error, the third law is valid for phosphine. Now we are going to discuss residual entropy. Residual entropy is a small amount of entropy which is present even after a substance is cooled arbitrarily close to absolute zero. It occurs if a material can exist in many different microscopic states when cooled to absolute zero. It is seen most often in substances which have very weak tendencies to align into their energetic ground state and which are cooled quickly. The first statistical picture of entropy was that of Boltzmann. The function W that represents the number of ways we can distribute n particles into a number of states. Using the function W, the entropy can be expressed as S is equal to Kb natural log W. Here Kb is Boltzmann constant. This can occur if it has many different ground states with exactly the same 0 point energy. It can also occur if the ground states have slightly different energies, but the system is prevented into finding and settling into the true lowest energy state. At 0 Kelvin, the system is in its lowest energy state. For a perfect crystal, there is only one way to distribute the energy and W is equal to 1. Therefore, entropy is equal to 0. However, the entropy is not equal to 0 at temperature equal to 0 Kelvin if the substance is not a perfect crystal. Although the residual entropy in such cases is a small correction to the entropy calculated for chemical reactions, it still leads to an important concept. The entropy at 0 Kelvin is known as residual entropy. There are number of substances that show similar statistical variations in orientations that lead to a residual entropy. A common example is the case of carbon monoxide, which has a very small dipole moment. As the carbon monoxide crystal is cooled to absolute 0, few of the carbon monoxide molecules have enough time to align themselves into a perfect crystal. That is, with all of the carbon monoxide molecules oriented in the same direction. There is a finite chance that CO will crystallize as CO, CO, CO instead of CO, OC, CO. For each CO molecule, there are two possible orientations in which a CO molecule can exist. So, the number of ways per molecule is 2 for each CO. If we have n CO molecules, there are W to the power n ways or 2 to the power n ways that all of the CO can be distributed. Therefore, the entropy at 0 Kelvin is equal to K natural log W to the power n, which is equal to n K natural log W. As K is equal to R upon n, therefore, we have S is equal to R natural log 2, and putting the values of R and natural log 2, we will get S, that is entropy, equal to 5.76 joules per Kelvin. Another example is any amorphous solid like glass. These have residual entropy because the atom by atom microscopic structure can be arranged in a huge number of different ways across a macroscopic system. With this, we come to the end of this unit, the second part of thermodynamics. In the end, let us revise what we have learned in this unit. In this unit, we discussed limitations of the first law and need for the second law, spontaneous or irreversible processes, statement of the second law, heat engine, Carnot cycle, entropy, Gibbs free energy, work function or Helmholtz function, Gibbs Helmholtz equations, conditions of equilibrium and criteria for a spontaneous process, the third law of thermodynamics, the Nernst heat theorem, determination of absolute entropies of solids, liquids and gases, and residual entropy.